Hello friends, welcome you all to session 16. So we will cover a few more things which I have missed, which is yet to be covered on the instructions front in this lecture. With this we will be completing all the ARM instruction set. So you are all equipped to start writing more and more programs using the assembly of ARM. Welcome to the world of assembly language programming. I hope you will enjoy this. So in this lecture we will be touching on interrupt latency, okay, especially what is the worst case interrupt latency for a typical scenario. I will explain the scenario and then I tell you how many cycles that would take, and then this instruction, null instruction, which I have not covered so far, so we will complete that, and then I will show a few examples, not many. With this we will be completing this lecture. So both these sessions will be completed. Okay? All these units will be done by today. So this is the focus of today's discussion. Okay. So what is interrupt latency? First, let me explain. I have told you earlier, but let us have a clarity on this now again. See, this is the processor. Okay. From an external unit, some interrupt is raised. Okay. Some signal, it could be a low. Some interrupt signal is coming in from external unit. So it would happen at a particular time t. Okay, t equals to 0. At a particular time t, it is happening because this is happening from the external hardware. It could be UART, okay, a serial port controller, or some other timer, or some peripheral which is running independent of the CPU. Okay, so it is generating an interrupt. It doesn't have any sense on where the processor is at that moment. Whenever it has completed its some particular programmed job, it generates an interrupt. So let us assume a signal which is connected to FIQ, that is a fast interrupt request. Okay, because the CPU is supposed to respond to this interrupt at the earliest among everyone. Okay, reset anyway is different because once the reset is accepted, the processor is starting afresh. So we are not concerned about that. We are worried about an FIQ which is connected to the system, okay, which happens to be very critical. And when this interrupt is raised, how much time a typical worst case scenario of an ARM processor responding to that interrupt is what we are going to see in this example here. Okay. So at a particular time in t, it has generated an interrupt. Now processor may be doing some job. It could be executing an instruction which is the worst case scenario, would be a longest instruction, which may be a LDM. Okay, I will explain that in detail. If such instruction is being executed, or any instruction being executed, ARM will respond to the interrupt only after the completion of the execution of that particular instruction. Please remember, because in the middle of the execution, if it responds, then it cannot know the how much of this instruction is completed, how much is not completed. So you cannot restart without any impact, impacting the correctness of the program. So to ascertain that the instruction which is being executed is not left in a halfway incomplete state, the processor completes the instruction which it has started executing and then responds to the interrupt. So when I mean by responding to the interrupt means it has to go to the interrupt vector table, okay, and then based on the FIQ, here FIQ interrupt, so it will have an entry here in the interrupt vector table to say it has to branch to the subroutine, which is a ISR, which could be the some handler, FIQ handler. Okay, so the time taken for the processor to complete current execution and then accessing the vector table and going to the first instruction, okay, executing the first instruction of the handler. Suppose it happens at this time, then this is called interrupt latency. The time taken for the processor to recognize the interrupt and then it is not enough if it recognizes it has to access the vector table, and then if suppose FAQ, you remember, it is the topmost in the table, so if the FAQ handler itself can start from here. If there is no need to have a branch. So let us assume the best case scenario where the instead of branching to the subroutine, FAQ can write the we can write the subroutine here itself, right? So coming here and start executing this first instruction of the handler is what the time taken for that is what is called interrupt latency. So this could be few cycles, okay, few M clocks. So we are trying to see what is the worst case scenario. That means what situation could cause the ARM processor to take the maximum time to respond to the interrupt or to execute the first instruction of the handler. See, the time at which the FAQ interrupt happens is independent. So it could happen just when the current instruction is being executed, right? It could happen, that is the best case, when the current execution is just completed and then the interrupt is happening and it recognizes, so it will immediately come and respond, within a 2 cycle it will start executing the instruction from the handler. So that will be the best case, okay? But we are here to find out what is the worst case. Why are we interested in worst case scenario? Because we are all embedded system engineers, so we are worried about what is the maximum time it would take for the processor to respond to an interrupt. We have to cater for that kind of a scenario, because though this is not going to be very frequent or it may never happen in the lifetime of the system, but the system should always be designed keeping this in the mind, because you cannot have a catastrophe just because when the interrupt happened the processor was executing a long instruction and then the system failed. We want a system which always works perfectly. That is the purpose of embedded system engineers, the designers. So we need to cater for the worst case scenario so that our system design is perfect. So let us see how we can achieve that and how long is the latency that is going to be, okay? And then we will talk about multiplication instructions and then a few sample examples, okay? Okay, before we start off with that, I want you to recall the key things that we learned in the previous discussions. So this is the relative priorities of interrupts. Now all of us should know by heart, okay? What is this order? Why reset is given the topmost priority? Because this is something has happened, the system has to restart. So we don't want the restarting of this system taking more time, because we don't want whatever being executed. It could be any of these exception handlers itself being executed right now, and the reset is given. Then it should stop whatever it is doing, the processor, and then it should start executing the reset handler. So that's why reset is given the most highest priority. Now you may wonder, we keep claiming that FAQ is the most important interrupt and it should be given top priority, but data abort is sitting on top of it. That means what? Suppose if an FAQ interrupt is happening from the external system, okay, at t equal to 0, and assume the ARM processor which is executing an instruction, maybe a load or store, LDM or STM, something to do with the data memory, okay. It was doing some memory access during that time, okay, using any of the load or store instructions or a swap instruction, right. So data abort can happen only when any instruction which is doing something with the memory is what will cause a data abort. Assume at the same time the processor is also doing a data access with the memory, and then it causes a data abort. So data abort could happen when the memory is notifying an abort signal, right. So ARM processor is doing a multiple memory cycle. It could do a multiple memory cycle if it is LDM or STM is done. So every memory cycle, at the end of every memory cycle, the processor is checking whether there is a abort signal coming from the memory. So assume that the worst case scenario is that t equal to 0, the absolute time. At the same time, and the memory cycle is also getting over, and then abort has been sensed. Already the signal has been raised by the memory, and then the processor notices that there is an abort. So why is that abort given more priority than FAQ? Any thoughts on this? Think it over. The reason I'll tell you the reason. Okay. See, when an abort happens, what gets notified? The exact instruction which is executing. Okay. Some instruction is getting executed, which could be a LDM, LDR, STR, whatever. So that instruction is causing a abort. Okay. So it is being executed. This one of this instruction is executed, and then PC is pointing at +8. Somewhere it is pointing. So now, if the OS or a handler needs to restore the content or remove the condition which has caused this data abort, and then it has to execute the same instruction again to make sure that it is completed properly, right? So to do that, it has to know which PC at which instruction has caused the data abort. So that should be captured and kept, right? That means it has to be in the handler's stack, or it should be in the R14 of the abort handler. Okay, R14 of the abort handler should have that PC value, so that handler can come back and execute it and then restore the conditions which caused this abort. So the PC value should be restored. That means what? It should be copied to this. If we don't do it at that moment, and just because in our scenario FAQ also happened simultaneously where data abort has happened, if you decide to start servicing this FAQ and ignore this, we have lost the PC, because PC will be now pointing to the FAQ handler, and then it will start executing the FAQ handler's code. So the PC which caused the data abort will be lost. Okay. So to make sure that this is restored, what happens is the data abort is responded to. Okay. That is why they have kept data abort more than FAQ. But please remember, it is not serviced fully. What I mean by that, it just enters. So suppose data abort has happened, FAQ also happened simultaneously. The data abort handler is just entered. Okay. That means what? The PC value which caused the data abort has been copied into R14 of the abort mode, and then immediately the processor comes back to handle the FAQ, because processor knows internally that both are enabled, both are to be attended to, because both have simultaneously happened. So it just only makes sure that I note down which address has caused the data abort. I will come back to this and then address it later. You may wonder, there is something to do with the data abort. How can we delay that? Please keep in mind the data abort has happened by executing some user code, maybe, or it could be some other handlers which are lower priority than FAQ. But let us, for completeness sake or for the explanation sake, let us assume that user code is being executed at that time. A data abort has happened, and simultaneously FAQ is also happening. Okay, this is data abort. Okay, and this is FAQ. So the reason for causing the data abort is something to do with the user's code, nothing to do with the FAQ or FAQ's handler. Okay, FAQ handler can be executed without any problem. Even it can have some load store or whatever. It may not have problem. The problem is only with the user code, where the user has put some value in some base register. Maybe it is R2. Suppose the user has written some address here which is not in the memory, so it is causing an abort. So you can always defer this, addressing this problem, compared to executing the FAQ handler. So you have to have a complete picture of what is happening. Then only you will know what is the reason behind giving a higher priority to data abort. At the same time, we don't complete the handler. The processor comes back to FAQ handler to complete it and then goes back. Please remember, this happens only when both data abort and FAQ happen together, and ARM has to service them. Now processor, just because the data abort is above the FAQ and it is for valid reason, so it recognizes the abort, it enters the abort handler but doesn't execute the handler fully. When I say it enters the handler, it has already taken care of saving the PC and the CPSR into the abort handlers R14 and the SPSR. Okay, please remember those things. 2 registers are being copied by the ARM processor automatically. So now you can defer this execution by now saving these values somewhere in the stack and then come back and then execute the FAQ handler. Okay, I hope this is clear to you. This is very important concept which is very difficult to understand. So what happens when both happen together? Let me summarize it. When both the exceptions happen together, ARM processor enters the handler. It doesn't execute the handler. It comes back to FAQ, completes the FAQ handler, okay, and then goes back and where it left off, it starts off. You may wonder how will it go back to this, because ARM processor, once it services this, the FAQ interrupt is disabled, not disabled, at least serviced. Okay, it is not pending. The FAQ interrupt is not pending. So processor tries to see if there is anything above this which needs to be executed. Okay, before coming back to the user code, it will encounter that okay, a data abort is pending. I have not serviced it, so it goes back to data abort. It completes the handler and then goes back to the user code which was executing the some LDM or SDM. Okay, so this is the flow of sequence when both of them happen together. Okay, that is a very unique situation which is not under the control of any of us. Very good. Let us now. So that is the reason why this is given more priority than this, and naturally this is given lower priority than FAQ because the system designer needs to make sure that the most critical interrupts which need to be serviced is connected to FAQ interrupt input, and the least priority interrupts are connected to IRQ. So based on that, you are prioritizing the order in which the interrupts are serviced. And the prefetch and user defined SWI is, I told you that it is for some running some operating system code. It could be for file access, or it could be for memory access. It could be anything. Okay, specifically any OS activities. So these are all programmed control flow changes, which is done by the part of the program as a programmer. So this can wait till these are handled. Okay, very good. So let us now. This is again, I have shown you this thing earlier. Please remember, setting this means it is disabled. Okay, what is disabled? IRQ is disabled. FAQ is disabled if it is set. So on entry to any of these handlers, okay, what is the default status of this I and F flags in the CPSR? That is what we are showing here. So I and F flag which are in it is in the order F and I, okay, in the CPSR, okay, bit number 7 and 6. So automatically the processor, as it enters the reset handler, it sets both of them. Okay, what does it mean? When reset has happened, we don't want to bother about whether the FAQ is coming in or IRQ is coming in. When the system itself is rebooting, there is no point in worrying about the interrupts which are coming. So ignore all of them, both of them, and then start handling the reset, whatever you are supposed to do on the reset handler. That's why the reset is given the highest priority, and both FAQ and IRQ are disabled. Now other things are very obvious. When undefined instruction or software interrupt or prefetch abort or data aborts are happening, FAQ is always given high priority. Now you wonder, even during the data abort execution, FAQ is enabled. Okay, so if you remember, recall in the priority, data abort was above this and FAQ was below this. Please see the sequence. This is the priority sequence, whereas this is just given in an order based on the vector table addresses. Okay, they are not in the order of priority. So though data abort is higher priority, but during executing the data abort handler, FAQ is unchanged. If suppose it was earlier enabled, it still remains to be enabled. That means data abort, during the data abort execution, FAQ can be serviced. That is what it means. Similarly, when prefetch abort is being serviced, that means it is working on the prefetch abort handler. If FAQ was earlier enabled, that means FAQ bit, that F bit in the CPSR was 0, that means it can get the first, if FAQ input comes, some peripherals give that interrupt, then it will be serviced, okay, in this status. But during reset it will not be serviced. But if it is already servicing an FIQ interrupt, one more interrupt comes on the same input, it won't be serviced because the previous handling itself is not done. So this is a spurious interrupt. It is being serviced, so it will not recognize that. Okay. So these are the conditions of the flag. So you can see that the IRQ is always enabled wherever which IRQ, even when it is servicing the IRQ interrupt, the another IRQ is enabled. Why? I will tell you the reason. Suppose IRQ is connected, please remember there are only two inputs to the processor. That means if you think that there is one peripheral and another one peripheral, okay, maybe this is peripheral 1, P1, P2, you should not think that only two peripherals can interrupt the ARM processor. Okay, that is not the ARM is designed for, or any microcontroller or a processor wouldn't have designed for only handling two interrupts or two peripherals. Then you may wonder, I have a system where I have ARM processor with so many peripherals, all of them can interrupt. How can ARM with the two inputs can service them? That is where the interrupt controller comes into play, which I have not explained. Okay, let me give you a short introduction to that. Let me take a new page. Okay, so ARM processor is there. There is an interrupt controller. Okay, IC, I am calling it as IC, that is interrupt controller. Okay, it will have so many interrupts connected to it. It not interrupt means what I am saying is the peripherals which could generate interrupts. Okay, so many peripherals. It's not only 4, it could be 16 or 32 or any number of peripherals. And then this particular controller itself will be accessed by the processor. Okay, this is ARM. It can through APB or some memory mapped IO, it will be able to configure this to say, okay, these are the peripherals connected to the controller. I want this to be given higher priority compared to this. So you connect the peripherals according to the priorities of the interrupt inputs that interrupt controller is programmed for. And then you can also selectively enable some interrupts. Okay, some inputs you can disable them. That means even if it generates, the processor will not recognize it because interrupt controller doesn't recognize it. Now the interrupt controller generate one single interrupt to IRQ. Please remember, processor will not come and check this every time. Hey, IRQ, controller, do you have any interrupt? No, processor is busy with its own job of executing its own instruction. So the limit of only two interrupts, two inputs which are given to the processor, one is FIQ and one IRQ. Normally FIQ is connected to a single peripheral device. Okay, it is a normal convention. The most important, okay, I should not put P1 here because P0. Okay, so this peripheral is so important, critical, that if it generates an interrupt, it should be serviced immediately. So it you connect it directly to that. Whereas IRQ you use it for connecting multiple devices to the interrupt pin. Now you may wonder, IRQ comes and then it goes to the vector table, right? And then it looks at the handler, it comes to the handler. Now handler has to know, okay, handler has to know which are these peripherals have created, generated an interrupt and which needs to be serviced in which order. So there is a priority maintained, and then based on the priority, the processor executes the ISR handler, okay, specific to the particular device which is connected. So the job of the interrupt controller is to monitor multiple peripherals connected to it and then generate the interrupt, and then the processor comes back and reads the status register or which are the interrupts are enabled. It looks at those register values in the interrupt controller, and then based on the values it takes a decision. Okay, I have both P1 and P2 now generated an interrupt, but I am most interested in P1 first. Let me serve the P1 first. Okay, and then it will, in the meantime, it will enable the IRQ and then go back. So what happens if one more interrupt is pending? It will again generate the interrupt, or the handler could finish up all the handling of all the interrupt and then go back. So it is all left to the individual implementation of the handler and the way how it is programmed, controller is programmed. So Please remember, interrupt controller is one level as a intelligent controller programmed by the ARM processor or the microprocessor, whichever is controlling the controller, and then the peripherals are talking to only the controller, and then through the controller ARM processor is notified on interrupt, and then it, please remember, the ARM after that it may serve the interrupt the sources directly. It has to get the data. Suppose serial port controller is there, it has to get the data from the individual devices. Only the controller comes into play to monitor and then create a priority among the generated interrupt. That is the purpose of the handler, controller. Okay. So good. Let us come back. So this is how it is done. So that's why IRQ is enabled even inside the IRQ handler. That is what I am showing. Okay. Very good. Let us now go forward. Now worst case scenario. Okay, the most complex exception scenario is FAQ and an IRQ and a third exception all happen simultaneously. Please remember, FAQ is also happening. Okay, IRQ is also happening. That means it has generated an interrupt signal, and then the execution, the current execution of some LDM, which is a worst case scenario, has generated an abort, data abort. Okay, so all of them have happened together now. It can happen. Please remember. Now, what does the processor do? Okay, based on the explanation that I have given you earlier, it is supposed to recognize that there is an abort. So it will execute, it will respond to the abort, enter the abort handler, and then it will not execute it fully. It will just enter the abort handler and comes back to FAQ. Okay, to act to work execute the FAQ handler. It will come back. That is the way it is programmed. The processor knows, okay, because this is active, and data abort is also active at the same time. Then it is supposed to enter the data abort and before the execution of the handler comes to FAQ handler to complete the execution. Now you may wonder, in this situation, after the completion of FAQ, IRQ is also there. Will it do this or do this? If you know the priority of the interrupt, data abort first, FAQ next, and then IRQ, right? So when these two happen, this is what is done. It goes to the data abort handler and comes back. But once FAQ is done, it comes and completes the data abort, and then only it will service the IRQ interrupt. So that is the order in which it is being handled. Okay. So the worst case scenario, you have to comprehend all this data. So FAQ has a higher priority than IRQ. So and then IRQ also is masked out. Please remember, it masks out the IRQ in the FAQ handler. So IRQ, even if it is generated, it won't be responded to. Ignored. IRQ will be ignored. So FAQ handler explicitly enables IRQ on return to the user code. Okay, on return to the user code only it enables. So till then, it won't be recognized. So FAQ is enabled. So data abort occurs same time when FAQ happens. The processor enters the data abort handler. That's what I mentioned. It enters it and proceeds immediately to the FAQ vector. Please remember, it doesn't execute that fully. It enters it so that it will recognize the address which has caused the data abort handler exception, and then it comes back to the FAQ vector. Okay, it executes the FAQ handler, and then on return it goes to the data abort handler. Resume execution. Please remember. So the data abort must have a higher priority than FAQ to ensure that transfer error does not escape detection. That's the reason. Okay, why it is given higher priority. Need to add that time now because this overhead is there. We have to add the time taken for coming to the data abort handler and going back. When calculating the worst case scenario for FAQ. Got it? Let us see. Now this is the timing I am going to show you. FAQ interrupt is passed through a synchronizer. What I mean by that, I told you that FAQ is connected to the processor directly, right? But there is a hardware, okay, a sequencer is there, which will take 4 cycles actually, okay? Since the time the FAQ interrupt is generated to the time FAQ interrupt signal, FAQ signal comes to the processor. Okay, this is ARM. Okay, so the sequencer job is to synchronize the time and then find out whether it is a spurious interrupt or is it a valid interrupt. So those kind of signal handling is done. So I'm not going into the detail of the synchronizer, but you have to comprehend almost 4 cycles getting elapsed before it gets into the ARM processor. So the longest time you have to worst case, you have to scenario, you have to enable, you have to comprehend this 4 cycle also, and then for having a worst case scenario of responding to FAQ handler, you have to think of a longest instruction being executed. Okay, that also the longest instruction just started executing and the interrupt is coming. Okay, after this 4 cycle, the interrupt is given to the processor by the time the execution of the longest instruction has started. Now you have to wait, the processor has to wait for this completion. The longest instruction I told you LDM. Okay, LDM also there could be LDM multiple load, but it could be a 2 register load also, or 3 register load, or it could be a worst case scenario of 16 register getting loaded. Okay, R0 to R15, all the registers are getting loaded from memory using the base register R2, because R2 is also overwritten in this scenario, but doesn't matter. It copies 16 values from the memory to the processor. Okay, so till it gets completed, the interrupt cannot be serviced. So you have to comprehend this also. So the execution time is 2 cycles. Before even start doing the memory access, you know that address calculation takes 1 cycle, and then putting the address onto address bus, address register takes 1 cycle. So 2 cycles are gone, and then maximum 16 cycles for every word to be transferred. Why 16 cycles? Because 16 registers are to be copied from LDM. Okay, so now we are thinking of a worst case scenario of a data abort happening during this execution, and FAQ is already waiting and data abort is happening. When will the data abort is happening? The worst case scenario of when the last R15 value is getting loaded from the memory, the data abort has happened. Okay, it is not completed, the instruction is not completed. Okay, but the data abort is generated, so it doesn't matter. Okay, once the data abort is recognized, the processor can come back and then execute it at a leisure. So only thing is data abort has to be recognized. So if that happens, then you remember I was explaining that if on data abort this instruction has to be executed after the data abort fix is done, the handler is executed, it will come back and execute the same instruction, right? So to do that, base register should be restored, because now I am telling you R0 to R15 means R2 is certainly overwritten here, right? So it has to be restored. So it will take 2 more cycles to write back that, keep that conditions of R2 with the updated value of, if this instruction would have been executed fully, what would be the value of R2 that will be written, not the copied value from the memory, so that the instruction can be restarted after the handler has done the job. So that takes 2 more cycles. So if you add up all of them, 20 cycles is gone. Okay, see, please remember interrupt was generated 4 cycles ahead, and then before that FAQ could come, LDM started executing, and this LDM also has not completed fully, and data abort has happened. Now because the data abort has happened, it has to restore the base register, and then it has taken 2 more cycles. Okay, so that is what that cycle, 2 more, the 3 more, this is 2 more cycles for write back. Okay, and then I told you that data abort entry has to happen. Okay, entry means what? It should just at least execute the first, access the first instruction of the handler. So that is also going to take 3 cycles. Why? It has to save the R14 value, right, in the PC which has caused this PC, which PC maybe +8. Okay, that needs to be saved in R14 of abort handler, and then current CPSR of the processor has to be copied into the abort handler's SPSR. So those things need to take, it will take some time, right? So 3 cycles elapsed. Now FAQ, now after that it comes back to FAQ handler, and then it will not execute immediately, right? 2 cycles, because of the pipeline delay. The first instruction of FAQ handler will execute after 2 cycles of the pipeline delay. So that is also have to be comprehended. Now add up everything. 2 plus 3, 5, 5 plus 20. This 20 comes from 16 plus 2 plus 2. So 25 plus 429. Okay. So it is not 1 or 2 cycles, it could happen 29 processor cycles, that is n clocks could elapse, okay, before the FAQ handler is executed. This is the worst case scenario. So hope you understood this. This is the most important. Now, if you understand this scenario, you will be able to visualize any worst case interrupt handling when you are designing a system, okay, and writing an interrupt handler. You can think about this worst case scenario in your back of your mind, and then accordingly decide what should be the cycle time of your processor and how much is the, okay, how will this convert into the absolute time. It is very simple. No, processor cycle is running as 1 megahertz. Assume how much of one clock takes 1 microsecond, right? So 29 processor cycle means it will take 29 microseconds, okay, before this particular interrupt could be serviced. Okay, so that is what I am trying to say. If it is a 2 megahertz, it will be double this. So I am sorry, it will be half of it. So this is how you have to compute the time taken for the handler to be executed, because that is the delay. Okay, worst case delay. The real time systems need to design such a system such a way that this particular absolute time is at the minimum, so that any catastrophe can be responded to immediately. Okay, good. So that was the most difficult part of this discussion today. So I thought I will spend more time. Now multiply and accumulate, you guys are already familiar. Mostly you must have executed multiply or divide operation using add and subtract. But now let us see the instruction mul supported by ARM. What is the syntax and how will they do? I will go a little fast. Now you guys are very familiar with all the instructions. So see, mul condition you know, yes you know, and then RD is a result where it is multiplied value is put and RM into RS. It should strike you now, okay, immediately that two 32-bit values are multiplied, correct? Here you can see that RM and RS is two registers which are 32-bit wide. It is written into one more 32-bit value. Is it correct? Will multiplying two 32-bit result into only 32-bit value? It could happen when you have values which are smaller, but if you have a bigger number here, you cannot fit in the result in a 32-bit value. You are very clear about that. You must be. It will at least take 64-bit, one more 32. But you may wonder what is the use of this instruction. This instruction is used only when you are bothered or only concerned about the lower part of the result, okay, not the higher part. You may ask me where are the reasons. No, there are so many in a typical scenario. You are interested in only knowing the lower value, or you may be knowing that my values which I am multiplying, they are not likely to be larger numbers, and I am forced to use 32-bit registers because ARM processor anyway has all 32-bit registers. But I may be doing a multiplication which is not even exceeding more than 100 in decimal value. Okay, so 100 into 100 worst case, how much it will be? 1000, right? Sorry, 10,000 it will be. So it it could be fitted into a 32-bit value. 64K is yeah. The 32-bit value will be easily able to accommodate that. But what I am saying is any number which aware of, which is whether it could be fitted into the lower value and you are not bothered, or you think that the higher values are going to be insignificant, or it is all going to be zeros or all ones. Why all ones? If it is a sign bit value, it will be a negative value, but significant part of it is only in the lower 32-bit result. In that scenario, you can always use this instruction, but you have to be very careful. Otherwise, you may have a erroneous result if you happen to multiply huge numbers. Okay, so the rest of the execution is very simple, and then one more instruction is called multiply and accumulate. What you do is we multiply two values here and then add one more register to the values in it, and then get the result. Okay, these are all useful for DSP operations. Okay, some of the DSP filtering, FIR, IIR, all those, if you have done a DSP course, you will know that there are MAC operations, multiply and accumulate. So this multiplication will followed by an addition is most often seen in the DSP processing. So what is the use of providing one instruction doing both? Because you are saving a lot of execution time. Because if you happen to have mul and add as a separate instruction, you would have spent one cycle executing this instruction and then one or whatever cycle time I will show you, and then add will take one more cycle to execute, and pipeline access, all that unnecessary power wastage, as well as the code size also is now one instruction occupies 32 bits, whereas this will take one more 50%, 100% more instructions, right, every MLA. So you are trying to optimize it by the processor has given you one single instruction for doing both operations. Okay, though add will take one internal cycle, but you are saving on code size, you are saving on time, power, everything. So only what you have to remember is this instruction supports gives you only the least significant 32 bits of the result. Similarly, that is also true with the MLA. MLA means it's not a number of, okay, it's nothing to do with the politics. It is multiply and accumulate. Okay, do not use R15 for any of them. Okay, there is no need for me to use R15, the code address, for doing some multiplication or addition, right? It doesn't make sense. So processor doesn't allow you to use R15 as one of the operands. And then RM and RD cannot be same register. Okay, these two cannot be same because multiplier and the multiplicand together. So you cannot overwrite that value with the multiplier thing. Okay, so that will affect the flow. So it doesn't allow you to do this. Okay, because the intermediate results it will be saving it internally the processor. So it doesn't want this to be a same register because multiplication doesn't happen together. Okay, it goes 8 bit at a time. I will explain you in the next slide. So for that purpose, RD and RM cannot be same. Okay, good. Now what are the other restrictions? I told you this both signed and unsigned can be operated on. Okay, the values in this register could be a signed value or unsigned value. Based on that, the result will be interpreted. But since you are only bothered about the lower 32 bit value, only the upper portion has the sign related information, right? So unsigned or signed will be changing only in the upper portion. The LSB portion will be the same in both unsigned or signed operation. Because of that, there are no specific two separate instructions for this, where the lower 32 bit results are given. So that's what I'm saying. Results of a signed multiply and an unsigned multiply of 32 bit operand differ only in the upper 32 bits. So lower 32 bits results are identical. That's why the same instruction could perform both unsigned multiplication as well as signed multiplication. What do I mean by this? As this instruction only produces the lower 32 bit multiply, they can be used. Okay, so same instructions are used. Whereas you might remember add, subtract. I told you that based on the flag, we have to recognize whether it is a signed or unsigned. It is left to the user based on the operand what the user has expected to have put in. Whereas in multiply, that is not the case because the multiplier itself needs to handle the signs accordingly to produce a result. Okay, multiplier hardware has to be aware of whether it is multiplying a signed value or an unsigned value. Okay, please remember that difference between a add, subtract, and then a multiply. So multiply needs to be aware whether it is doing a operation on a signed value or unsigned value. That's why there are two separate instructions which are put in the later part of the the next slide I will be showing you. But in this case, it doesn't bother about it because the LSB part of the result is always same. Okay, whether it is doing a multiplication of each type. So it may assume one of the type and then perform the calculation. Okay. So what is the cycle time? So cycle time is 1 S it will take because pipeline execute state is 1 S. Okay, because during that time one fetch is happening. So 1 S anyway it will elapse. for executing the instruction. Now, how many internal cycles are done? M internal cycle. What do I mean by M? M is the number, okay, either 1 or 2 or 3 or 4 based on what is the value on this part of the multiplier operand. See what I mean by this, I'll let me explain you. This is multiplier, okay, multiplier into multiplicand, okay, multiplicand, MD I am saying, okay, and this is the product. Now multiplier based on whether it has got, okay, this can be split into 8 bits, okay, whether it has got a significant value only in the lower part or halfward part, or it has got the least LS 3 bytes or 4. Based on that, okay, the amount of time it takes will increase. Why? Internally the ARM processor does a 8-bit multiply. It has got a 8-bit multiply. So what it does is it is taking one 8-bit at a time and then multiplies and then put the result and accumulates it. So if suppose you have a value which is different bytes, okay, a 32-bit value can be split into 4 bytes, right? So if they are all zeros and then only some value is there which is maximum 255, right? Yes, sorry, if it's an unsigned value, it could be unsigned value also. I must guess 255. Otherwise, it will be plus or minus to 127. Okay, minus 127 or plus 126. So based on this significant value, if it is only 1 byte, it can do only one multiplier, 8-bit multiplication, and then the rest of it is all zeros or all ones. All ones means is the negative value, okay, and only this is unique. So it has to do only one internal multiplication, okay. Let's say 1 is there. If it has got up to this point, it has got some significant numbers, and then these are all zeros or ones. Only the top portion is zeros or 1. Please remember these numbers, okay. Note down the numbers, okay. So in that case, it has to do a 2 multiplication. So internal cycle either it could be 1 or 2 or 3 or 4 based on the number. So it is. So you cannot say particular instruction will take this much time. It depends on the value that you put in inside RM. Understood? So every time when you put some different value, this instruction may take different time, different clocks, number of clocks, which is decided by the number that you are putting into the RM. So that's what I am trying to say here. Okay. So apart from multiplication in the MLA instruction, one addition is there, which is also the addition also depends on this value, okay, whether how much significance it is, whether only one 8-bit addition or no, because it is done along for every addition, multiplication addition is also done, so that will also go through the same thing. But one additional cycle is anyway there because of the one additional anyway it has to perform an RN access, it has to do, okay, even if it is all zeros, it has to perform an addition. So that one cycle is taken and then other things are decided by these values, okay. So I hope this is clear to you. Now one more instruction, set of instructions, it is multiply long. What does it mean? Let me explain this. Here unsigned long, okay, the unsigned or signed is specified by the instruction. It will be corresponding to some bit in the instruction encoding. Condition flag is there, yes flag is there, okay, I will not explain again, all of you are familiar with this. Now you see this, there are, see, though it is RD low, RD high, these are nothing but one of the registers R0 to R14. Please remember, we can't have R15 in the multiply instruction. So you can use any one of them, okay, as this, and then RM and RS is there. In that case, what will be the result? How is this computed? RM and RS is multiplied and the lower word of the result is put in RD low and higher word is put in the RD high. What I am saying is you could write an instruction with the R1, R10, R11, R1. Okay, you can have anything. Sorry, here what did I put? R1 I put, I think. So let me put R4. Okay. Now what happens? The result is put in, the higher weight of the result is put in R1, the lower word of the result is put in R10, R11 and R14, R4 are multiplied, and then result goes here. So the choice of these registers need not be in any order, it could be anything. Only thing is you better make sure that they are all different so that you don't get a result which is totally absurd. Okay. So now if you are doing a signed arithmetic, the same thing. Okay, these numbers are interpreted signed, and then processor internally does the multiplication accordingly. And then if it is unsigned, and A accumulate is also there. Now what is the difference? This result is added. Please remember these two are same. Why they have made it? This is the usual usage, okay, in a typical applications, DSP applications. And then moreover, if you need more registers, then if these two are to be different, you will have totally 6 registers being used, and 6 registers is different registers you want to give. You need a 4 bits for encoding those values. Okay, so 24 bits will go in that only, in encoding these registers. And then remember, condition flag will have one 4 bit is gone, and then S bit is there, one bit is gone. Then where is the space for you to accommodate this in the 32 bit instruction bit? So it is not practical to have all these registers separate. So it is all given same register, it is implicit. Whatever register numbers you mention here, that will get added here as a when you mention the accumulate instruction. So same thing is done for some find value. So that's all about. Okay, R15 should not be used. Okay, so no, you cannot use R15 as an operand. And then RD, RO, RM must also specify different registers. See, please remember, RM is also should be different register, and that is for the correctness purpose, and even for executing the instruction. And the UML and SML are either unsigned or signed. Okay, and the result is a 64 bit value. Lower 32 bit is there, and the higher bit. So UML and IML instruction treat all their values as unsigned or 64 bit value. SML treats it as a signed 2's complement number. Okay, so this is how it does. Multiply, accumulate, adds that value. The 64 bit result will be added to the multiplied value, and then the 64 bit result will be put. Okay. So the lower 30 bits of the 64 number to add is read from RDLO. That's what here. Please understand that 32 bit, lower 32 bit of addition coming from here, higher 32 bit of addition comes from here, and then this is multiplied and then added to this, and then the result 64 bit value is put into the registers. Okay. So we have come to a end of multiplication. Okay, I hope you understood this. It's very simple. You try out some simple number with the simulator, and then you will understand where the results land into. Okay. So cycle, instruction cycle, it is similar to what we saw earlier. Only thing is there is m+1 here and m+2 here. Okay, I am not going into the details of this. And m is again decided by these numbers, which I have already explained to you earlier. So this additional 1 is there in both the places because it is a 64 bit. Okay, so there is additional delay of one more internal cycle because it involves a 64 bit addition. Okay, it's not only bothered about so you have to, it has to spend one more cycle in copying this value into this register. Please remember, in the register file, the results have to go from the multiplier unit to each register. So there is only 2 read port, write port, right, for the register file apart from the R15. So when there are so many parameters to be accessed, operands to be accessed, and the results will be written, and it's all 64 bit value, so 2 registers are accessed, so you will have additional 1 cycle of extra internal cycle to put the result back into the register file. Okay, so these values are similar to the value that you have given in the multiplier, whether they are significant or not. Based on that, it takes so much of time, and again it depends on the multiplier only, nothing on the multiplicand. It doesn't depend on the multiplicand or the add the offset or whatever addition is being done. Okay, Very good. Now I am not going to show too many examples because we have seen a lot of examples while studying understanding those instructions. I want you to try out all the instructions because we need time for covering other portions of the ARM code. So I am restricting this to just a small examples. Okay. So it doesn't save a lot of execution time, but that gives you some optimization. Okay, how some different code can be written in a different way. It will give you a clue. Okay, it depends on your imagination and how much you understand the instructions. So that I want you to use your innovative skills to write optimum code. When I say optimum code, you should be able to perform job with a minimum number of instructions. Why is it good? Because if you can perform the operation in a minimum number of cycles, you are taking less execution time and less amount of code size. So suppose this is the condition. Okay, if Rn is equal to some value P or Rm instruction, okay, some register, one of the registers is equal to Q, some immediate value, then go to label. If you understand the C convention, okay, if this is a typical C code, what does it do? If this is true, okay, in an R condition, what does it do? It doesn't even evaluate this. Why? It doesn't matter, right? When you have this true, whether this is 0 or 1, okay, this is 1 already you have said. If you are it, what are you going to get? Here also 1, there's also 1. So it is a don't care, correct? Irrespective of this value, you are, once you know that first condition is true, you don't have to evaluate it. You may wonder, what do we gain by not evaluating? Please remember, in this case it could be a simple assignment, okay, but as you are aware, a C allows you to put a complex expression here. It could involve some multiplication to addition to memory access to anything. In that case, if performing this operation involves so many instructions, assembly instructions, and which will all involve some cycles. So no processor or no language doesn't want to execute or waste time which is not relevant and which is not going to affect your correctness of the code. So unless you have any dependency, you are not supposed to have the dependency also, because you have to remember that in a language in this like this, if this is true, this may not be executed at all. So you should remember that when you are writing the code. Okay, as a caution I am telling you when you are writing C code. So let us come back to assembly now. Now compare Rn with P. This is the job being performed. So this Rn is not disturbed, please remember. And here it is not assignment, okay. I took it from the book, so please remember it is just a comparison. You know, if it is equal to. So that is what it is, a pseudo code. It is not a typical C code, okay. So it doesn't assign the value P into Rn, okay. If that assignment happens, then this compare, what does it do? It just compares it. It is not assigning this value into Rn. So please remember, the intent is not to assign the value, it is only to compare the values. So this is the right choice of the instruction. And then now what is done? BEQ, that is branch on equal. If this happens to have resulted in a 0 flag being 1, okay, 0 flag being 1, then you can just jump to label. Label is not shown here, it comes somewhere to label, okay. So this will not be executed. That is what is required also, right? C also, if it is true, it will just go to the label. It will not execute this instruction. So that is true. It is in sync with the what is intended by the language. Now suppose if this turns out to be false, then it has to execute this instruction. It has to do a comparison. Now will it happen here? Let us again check. Yes, if this is not true, the branch will not happen, because it is only the conditional jump branch. Only when it is equal to this jump would have happened, otherwise it will execute this instruction. So what does it do now? It compares Rm with the Q, okay. Now if this is equal, it will jump again to label, okay, the same location. Otherwise it will fall to the next instruction, which happens to be here. So it does the job, you agree, but there is an optimization possible. I am not asking you an example because I have given you the code here. Maybe if you want you can take a 2 minutes break here, okay, and check whether these two are equal, okay. This 4 instruction is compressed into maybe 3. Are they same? 2 minutes break. Welcome back. You should have convinced yourself now because it is taken from the book and I am saying that they are same, so you should better agree. Okay, let us see whether your explanation matches with mine. What is CMP? It is executed with no conditions, okay, always, okay. So it executes. Now will it impact the flags? Of course. Which are the flags? Our favorite C, Z, N, V, okay. All flags are affected. I am not saying whether it is 0 or 1, they are all affected. It is reflecting the comparison value. Now compare NE. What does it mean? NE means not equal to. That means it is only bothered about this particular flag. Suppose if it is not equal, that means if the previous comparison what was performed was not equal, then 0 flag would have been what? 0. It would have been equal to 0. Then NE will be true. Then compare NE means what? Only if the previous comparison happens to be false, you execute this instruction. Who execute the instruction? Not you or me, the processor. So the processor should execute the instruction CMP only when NE is true. That means previous comparison has resulted in a false, right? That is what we want. If this is false, we want this to be executed. Isn't it doing that? So you may wonder what is the advantage. See, one branch instruction is avoided. It directly goes to this branch instruction. You may wonder, see, anyway in my case also this was not executed, right? The previous case also it went there directly. Now what is the advantage? First of all, the code size is saved now. So you have saved one word of instruction, okay. You have not removed this, but you have removed one label. And then how much time, extra time you are spending? One cycle in the pipeline, okay, because one instruction, this compare instruction has come into the pipeline and then it is not getting executed if this happens to be true. Otherwise it executes this instruction and then jumps to label. So in this case you may not see the benefit so much in terms of execution time, but you can see in code size it is saved. But actually you can save it in a different way. Suppose if you don't put the label here and then actual content itself if you put here, one branch instruction itself can be avoided, okay. So that will be a very good in terms of pipeline optimization. That means if I say, you know, you fall through in this instruction itself, then this one branch to this, okay, could be avoided. That means the pipeline flush and then restart could be avoided. So it would have been a very beneficial in terms of execution time. But in this case, what you save is the code size. Okay. I hope you understand the advantage of this. It's very tricky but very intelligent way of coding. That is where ARM scores. Okay, ARM processor has given you a lot of ability to use this instruction effectively. Okay, one more example. Again, you can take 2 minutes break. I want you to tell me what is happening here. Assume there is some value in Rn. Okay, I want to know after this RSBI what will be the value of Rn. Okay, what is the relationship between the value in Rm before and after the execution of these two instructions? Okay, that is the question. 2 minutes break. Okay, let us try to see what happens. TEQ, what does it mean? It checks whether Rn is same as 0. Okay, whether Rn is given as 0 value. Okay. Now RSB, you know that reverse subtract. Okay, you should have by now went back to the manual and then referred what is reverse subtract. I don't know whether 2 minutes would have been sufficient. If you don't remember, recall what is RSB. Okay, reverse subtract. Okay, what does it mean? Normally a subtract instruction. Okay, subtract, sorry, sub RD. Okay, RM. Okay, RN. What it will subtract? RD is equal to, very simple, right? I told you how to write this equation without trying to recall from your memory. So this is the job. Now suppose same thing is given as RSB. Okay, what will it do? It will swap these two. What I mean by swapping means it is not swapping the contents, it is swapping the way it is taking the subtraction. So Rn minus Rm is equal to RD. Correct? You should know by now, you should know this, but if you don't remember, please. Now you tell me what is happening here. Subtraction is happening between an immediate value 0 and an Rn. Normal subtract would have happened Rn minus 0, but here it is 0 minus Rn, and then the result is RD. Okay. Now on what condition? If it happens to be Mi, Mi is what? Minus. So what I mean by minus? If Rn was minus, that means what? When the TEQ was done, the flags, which are the flags affected? CZ and V, our friends. So N is set, that means what? The sign flag is set. Then Mi will be true. RS will be executed. That means if this Rn was negative, Rn earlier it was a negative value. We are worried about the sign bit value. So if N is set, that means Rn was negative. Now when we do 0 minus Rn now, which is happens to be a negative value, what are you supposed to get? Plus Rn. That means it is a mod of, what I mean by, this is what you are going to get. The positive value of Rn, if it happens to be negative, will be there. But okay, if I hope you understood this. Now, if Rn was negative, it will subtract from 0. That means it will just do a 2's complement of that number itself, which will result into a positive value, which happens to be the magnitude of that negative number. Okay, so it will get the magnitude of the value. Now you may wonder, if suppose Rn was earlier negative, positive itself, it was always positive earlier, will it impact the Rn? It won't, because Mi will not be 2, so RSB will not be done. So Rn will be same as what it was earlier. So irrespective of whether it was positive or negative, you will get the positive value in the Rn. If it is negative or if it is positive, you will get the same value. That is why I am saying it takes the absolute value of a negative number. Otherwise, it gets the same positive value. So see how, actually in a C code you will be writing it in a big assignment, right? If C is equal to, suppose I is having is assigned value. If I is less than 0, you will say I is equal to I. Sorry, I'll write it like this. I is equal to minus I, right? You will do this much in the C code, whereas it will generate only this much of assembly instruction in the finally by the compiler. Okay, so optimal, right? Almost like one assembly instruction per one higher level language instruction. So it's pretty unheard of. Okay. So that's the power of ARM processor. Very good. Now you may take 5 minutes break now. So this is the last problem of today's class. So you can take a long break after this. So please spend some time understanding this instruction. This time you should get it right. If you didn't get it right the last time, okay, take a 5 minutes break and come back. Welcome guys. So what did you learn? So I am not going to explain, the slide will explain. if the above example, if RB has either 4 or 5 or 6, RB is what? See, please remember, I have put RB, RC, RA doesn't mean that you can write the same code in the assembler in the simulator and expect it to work. Why it will not work? RB and RC are not, RA are not understandable by the assembler. You have to convert it into some R1, R2, R3. But I have put it to tell you that which registers are common across them. Okay. So you have to replace them with some specific registers R1, R2, R3 or whatever you like. So please don't put R15 there, and then try to execute this instruction and see what happens. Okay, to yourself, and try to understand what these things mean. So carry set, this is high. High means this is, see, this comparison is, if this is true, this will be true. Okay, and this is true, this will be true. Okay, so it's basically based on the value in RB. Okay, it multiplies based on the value in RB. RC is multiplied either with this or this or this, but you see, you won't see any multiplication at all. Okay, multiplication is a costly operation, whereas just with the move and LSL, LSL is what? Left shift. Left shift by 2 bits means it's a, if you shift it by 2 bits, it is equivalent to multiplying by 4. Okay, agree? So after that, it is either you want to multiply by 5 or 6, which can be done by one addition, extra addition. Please remember, right? Suppose you want to 5 into 6 you want to do. I can do it in 2 ways. This 5 itself, what I will do, I will shift it by 2 bits, which is equivalent to 5 into 4. So it is equal to 5 into 4. I have already calculated, but my interest is to multiply it by 6. So instead of multiplying it by 6, I multiply it by 4 by shifting it by 2 bits, which is a very easy operation and takes less time. And then I add one more 5 and another 5 if suppose if it happens to be 6. I will only add 5 if suppose if this multiplication was only 5. If it is 6, I will add one more 5. So 2 addition is just 2 internal cycles, whereas multiplication takes more cycles. You have seen that M into I, all that you have seen, right? Based on the multiplier value. So multiplication instruction is much more costlier than performing an addition. So we are performing this addition, that too based on the data value. So number of cycles wasted are very less. So this is very optimal implementation of a multiplier. So this I am giving you ideas so that you can write such a code and cut yourself. Okay, very good. So RB is less than 4, you multiply it by 4. If more than 6, it will also be. So if it is less than 4, it will be multiplied by 4. If it is more than 6 also, it will be multiplied by 6. So that is also you should remember. It's not that only 5, 6. It could have a value which is lower than this or higher than this. Even then, this is the operation done. Okay. So, and we are coming to the end of all the instruction set. Okay. Next class we will be covering thumb mode, which is a thumb state, which I have not talked about it, but though we have seen few examples using them. So we will talk about that in the next class, which will be interesting topic. So with this we are completing all the multiplication and some few examples, and the interrupt latency we covered it in detail. Please understand this fully for you to have a clarity on interrupts, how they are handled and how the exceptions are handled. Okay, I hope this was useful to you, and go and try it out on the simulator and have a nice day. Thank you very much for your patience listening. See you next class. Bye bye.